He's just recently finished his PhD at the University of Manchester, where he was working with Dr. Richard Babby. And his general field of research is numerical field theories and solitons, and also parameterizations of modified gravity, which he'll be telling us about. Thanks.
Yeah, thank you very much for the invite to come here and talk to you today. Visiting perimeter, so while I was in town, so I can give a talk. Yeah, so this is a talk on some work I've been doing recently with Richard Batty, my old supervisor. We continue working together. It's work based on a bunch of papers. This top one is in JCAP, it was published a while ago. There's a conference proceeding which is sort of slightly shorter. This is quite long, it's about 50 pages, but this is only 4 pages, so it's good to get a quick overview. And then a paper we put out very recently on a sort of an interesting subclass of formalism. Yeah, so this is where my talk is going to go. Very brief introduction to cosmology and the dark side. What is it? What are the current approaches to parameterizing ignorance? So there's this dark sector. How do we go about trying to observationally understand what it could be? And then we'll just straight into our formalism and our approach. Hopefully, after pointing out some of the perhaps flaws in current ways of doing things. And then quickly show how our thing connects to massive gravity. So this is something which has become very popular very recently, and a really interesting way to interpret massive gravity. And then finishing up, I suppose, or the culmination of the whole project is writing down equations of state for dark sector perturbations. It's basically how many versions of W do you have for perturbations, for modified gravity, and importantly, what do they actually mean? And how can you go about observing them? So this will have some plots in it, and this is mainly maths. And then where are we actually going? What's there sort of to do in the project? Okay, so this is very briefly cosmology, I suppose. So if you take Einstein's field equations with the F1W metric, so you assume homogeneity and isotropy in the background, with some perfect fluid with a density and pressure, stick it into the field equations, so assuming general relativity for the gravitational theory, you get a bunch of field equations which, when you solve them for a known matter content, a known pressure and density, it tells you how the scale factor of the universe evolves. It tells you how distances evolve in the universe. And you can also do it for fluctuations about the homogeneous isotropic universe. So now you can end up getting predictions about how the perturbed geometry of the universe looks, which basically tells you how structures should evolve in the universe. And all of this formalism basically gives you a set of predictions for distances to things, so how far away are supernovae, for example, what should the cosmic microwave background fluctuation spectrum look like, what does structure look like in the universe. Basically you use this a lot to get a prediction, for example, for how many galaxies, how much structure should you see of each size in the universe. And these are all things which we have measured to varying degrees of accuracy. So in some sense, to pull together the standard model of cosmology at the moment. At the moment, you'll see what I'm going in a minute, but I'm not putting dark energy in here yet. So you say, okay, we've got general relativity for the gravitational theory. This is how gravitational physics works. An F1W metric, so homogeneity on large scales. Standard matter content of baryons and photons and neutrinos, things like that. This is a model, it's a theory. You take that, you combine it with some data. So we've got the theory, and then it gives you a set of predictions. You go away and you observe it. You take photos of the universe, and you find that the two are massively inconsistent by a long way. Hopefully this is not news to anyone. So what went wrong? Which part of the ingredient, which one of the ingredients in the cosmological cookbook needs to be re-examined? So one of the parts was gravity. We assumed general relativity was the gravitational theory that described the universe. Maybe general relativity is not the gravitational theory that we should be using on large scales. Applying GR to cosmology is just an assumption of the validity of GR as the gravitational theory. It was developed on solar system scales, has been tested exquisitely well on those sort of scales, but extrapolating upwards to the whole universe is an extrapolation. We don't know if it holds. The geometry of the universe, maybe the universe is not actually homogeneous and isotropic on large scales, in which case you need to think about inhomogeneous universes. Well, the content of the universe, maybe there's more to the content of the universe than we realised. So this is where dark matter and dark energy come in. So dark matter approximately was invented for structure formation and galaxy rotation curves, whereas dark energy is invented to understand as an understanding of cosmic acceleration. So we're in some sense to marry up the model and the data. We've got three options really: modified gravity, inhomogeneous universes, or introducing some more content. So this is the way that's usually taken. Assume that the universe is homogeneous isotropic. Assume that GR is correct. And then what we require for consistency between the model and the data is to invent about 90% of the universe. We need to invent 24% of the universe to be dark matter, and 73% of it, or thereabouts, to be dark energy. We require them, and it's entirely an invention. And then it works. The dark energy has to have a particular equation of state parameter W, which is less than minus the third. Raises the massive question: what is the dark energy? What sort of substance has an equation of state, which is like anti-gravity, which actually repels things? What is it? Or perhaps the observed acceleration is actually a manifestation of non-GR physics kicking in on large scales. This is a nice sort of historical precedent in some sense. So about 100 years ago, let's say, we didn't have GR. What we had was Newtonian gravity. Newtonian gravity was constructed and was tested to really high precision on the Earth and the solar system, except when it came to the planet Mercury. So the Newtonian calculation of the Mercury-Sun system didn't work. Mercury has a wobble in the orbit. And so in the 1860s, Urban Leverrier invented the planet Vulcan, and so that the Newtonian calculation of the Sun-Mercury-Vulcan system works. It's just that the planet Vulcan doesn't actually exist. It was actually the Newtonian gravity theory, which doesn't exist. I'm giving you half a story. He also invented the outermost planet before Pluto to fix the orbit up there, so Neptune and Uranus. But the point is that Newtonian gravity was never designed for such a high curvature extreme regime, and so that invented the whole planet. Today we're inventing 96% of the universe because we've taken GR to be correct on the whole universe scale, which of course raises what is the gravitational theory that describes that works on cosmological scales. Of course, GR, or something like GR, has to kick in at solar system scales, and where we've tested it in the strong field regime, but we don't really know what happens on cosmological scales. So what is the gravitational theory? So again, to bring it home, I suppose, so the accelerating universe can be thought of in terms of either dark energy, so some content. There's some correction maybe due to inhomogeneities, which when we're missing, we're interpreting it as cosmic acceleration. Modified gravity, so a good way of thinking about modified gravity, so this is non-GR gravitational physics, is that the same matter content causes gravity to respond differently. So the same stuff will generate a different metric, crudely put. So what we'll call it as the dark sector. It's something that causes apparent acceleration. And there's lots of dark energy modified gravity models. So I'm only going to focus on dark energy modified gravity here, not in homogeneous universes. There's been a lot of models constructed, dark energy modified gravity models, in something known as ZOO, so the cosmological constant. It's probably the simplest, but it is the simplest. Where you just add a constant term as the action. Quintessence, where you had a homogeneous canonical scalar field, is the action. K-essence, where you had a scalar field with a non-canonical kinetic term. So a canonical kinetic term, for those if you're not aware, it will just give you half phi dot squared in the Lagrangian. This will be canonical scalar field theory. Non-canonical will be some function of this thing. So that would be K-essence. Galileo, which is another scalar field theory with high numbers of derivatives in the Lagrangian. It's just the Lagrangians are constructed such that the field equations are second order to avoid ghosts. F of R theories, where you introduce arbitrary functions of the Ricci scalar into the action. Something called elastic dark energy, which I'm going to come back to later, hopefully. But basically, it's a theory where you treat whatever the dark sector is as some sort of elastic medium, and the elastic medium has ends up giving you the right sort of properties to produce cosmic acceleration. Massive gravity is another model, Einstein ether, where you introduce a vector field into the action. All of this stuff is basically what I want to call Lagrangian engineering. You take normal GR and you keep adding bits onto it, making it more and more complicated, adding in more and more functions and parameters to try and describe what it is that you end up seeing. It produces models, so it's what I call Lagrangian engineering. This is a wonderful review of modified gravity theories. It's about 300 odd pages long. It's really great. I recommend it. So here's a few of the Lagrangians from the model Zoo. Cosmological constant, as I said, so you get the Einstein-Hilbert term, just the Ricci scalar, and you add on constants, f of r. You can add on whatever, some functions of other curvature invariants if you want. Quintessence, as I said. This is f of r plus quintessence, and k-essence, where you have some functions with the kinetic term. This is Einstein ether theory. We have a time unit vector with a Maxwellian kinetic term. You can generalize kinetic term, people have done that, but a generalized Einstein ether. And there's many more Lagrangians. This is all what I say is Lagrangian engineering. It's rather there's no real elegance, I think, in this sort of way of going about things. Yeah. Okay, so hopefully we can now see the problem. There's a lot of theories, but what we have is a bunch of theories, and what we also have is observations of our universe. We have the universe, we have photos of it. We have observations of things like the CMB, lensing, gravitational lensing of the CMB, structure formation of the universe, Parameterizing, acoustic oscillations, light-scale structure, etc. And so what people do is they write down their favourite theory and they work out what sort of universe it produces. And if it doesn't produce the same observations, you bin your theory, or you change your parameter, or you add a new function. But what people are starting to do now, well, that's like trying to pin the tail on the donkey, trying to get in the right place with a good guess. What people are also starting to do now is taking observations and using it to tell you what sort of theories could be realised by nature. Because it may well be that a bunch of these theories actually have identical looking universes. You wouldn't know that. So this is a popular way that people are going about it at the moment. So this is the Canada, France, Hawaii telescope lensing survey paper which came out recently. I've got the archive number up in a minute. Basically, the idea is that they want to use data. They're using data to say to put some constraints on what the modified gravity parameters are allowed to be. So in the conformal Newtonian gauge, you have two Newtonian potentials, psi and phi, and in general relativity, there are particular values. If GR is not the gravitational theory in the universe, then the one you actually observe will be some correction to the GR version. And there's two combinations. There's phi itself, and then there's the sum. So they're parameterizing the actual deviations that you see with two functions, mu and sigma. And what these guys did, they wanted to work out what sorts of functions of these are consistent with data. If mu and sigma are both exactly zero, then you get back GR, or I think it's GR plus lambda CDM. So what they do for simplicity, because they're trying to do data analysis with this, they can't parameterize for absolutely everything. They'll pick scale invariant versions of these functions, so sigma just becomes a function of time, or the scale factor, and then they parameterize out the time dependence by pulling out the omega lambda terms and just having two parameters, just simple numbers, sigma naught and mu naught. And then they go away and marginalize these parameters over the data, or different types of data. So these are confidence contours and what sigma naught, mu naught is allowed to be for different types of data sets. So what they're doing in here is basically honing in on a GR, a set of parameters consistent with GR. Now what they're actually doing is honing in on GR with some error bars. So there is some error bars around this. And in some sense, this highlights the point that what they're doing here is understanding what values these parameters are allowed to be could be realised by nature, but it doesn't tell you anything about what sorts of theories have these sorts of parameters. For example, I went away and computed what the value of this coupling function is, mu, here, for a scalar field theory. And so this is over scale and over redshift, and so this is the GR value, and it deviates at late time and large scales by only a few percent, is the point. So this is a very sort of generic, this is rather robust in the changeable parameters. But the sort of change you're going to get in mu here is only by a few percent. Even though it's quite a different theory to GR lambda CDM, it's more of a quintessence model, it will still be completely consistent with here. So these parameters aren't really telling you about whether these sorts of models are ruled out or not. In some sense, this is the problem. People are producing constraints on parameters, and it's not clear what it is that the constraints actually tell us. Do theories actually produce large deviations of these parameters or not? Because if theories produce basically the GR values anyway for these particular parameters, then constraining parameters is not going to tell you anything about what sort of modified gravity theory could be realized by nature. So this is the archive number for this CFHD paper. So what we would like to do, where we're going with this, is to construct a good phenomenological link between theory space and observations. We're taking input from theories, what sorts of theories can be realized by nature, what sorts of observations of nature do we actually have, and creating a toolbox to connect the two. So we can say something about the theory space, which is actually realized by nature using observation. Where I'm heading with this, so now getting into sort of my formalism, I suppose, is we're going to construct a meaningful way to describe an observed phenomenon. So we have images of a universe. We have the observed phenomena. We want a way to describe it. We want a way to understand what sort of physics combines to construct what it is that we see. There are various people who are doing this sort of thing, and we're very much caught between the tension of theoretical generality and experimental feasibility. So what you can go away and do is construct a parameterization which parameterizes over everything you've ever thought of and anyone's ever thought of, in which case you will be utterly theoretically general. But you'll have a billion free functions and you'll never be able to do anything experimentally. So what we're trying to do here is construct a workable parameterization. And the rest of the talk is saying how we do that and what it actually gives us and what it tells us. So this is, in some sense, is our philosophy. There is a lot of theories in this model zoo, and that is quite bad. So what we want to do is identify the freedom within those theories that actually affects observables. So here's all these theories. How do they actually combine to produce a universe? And we're able to study wide and general classes of theories and boil them down to regions of some parameter space. So these bunch of theories, the way that they affect observables is just encoded by the values of two functions, two parameters, or however many it turns out to be. But it's these parameters which actually go away and actually affect observations. And theories in parameter space may well be degenerate. So a bunch of different sets of theories may well produce identical sets of these parameters. And it's the parameters which you can observe, not the. In which case, you can't do better than that. So what we'd like to do is, this is very schematic at the moment, is formulate all the equations for linearized perturbations in terms of, for example, two of these parameters which we'll figure out. So looking at linearized perturbations in the universe, there's a good reason for that as opposed to the background, and I'll come to that in a bit. It's these parameters which will end up constraining with data, and the way that we've formulated everything, we can trace all these parameters back to some interaction term in the Lagrangian to trace something about symmetry or something like that. So for example, you find that everything is characterized by the values of two parameters, P1 and P2, and then you can go away and compute what the values of these two parameters are for your favorite theories, and you find out that theory number 1 occupies this particular region, etc. But then you might find that data favors some region that sits like that, so that immediately tells you something. I'm going to be much more specific later on. I just want to be a bit. This is our philosophy at the moment. This sort of thing happened with particle physics in the 60s and 70s, by the way, but it hasn't really with cosmology. Particle physics sort of realised they had all these theories. They want to figure out how all these theories actually combine. What are the things you actually observe with an experiment? And that's what we're trying to do here. Right, so how are we doing that? We're doing that with an action for perturbations. So one of the things that we do is we work out our parameterization for a particular field content of the dark sector. So we'll say, okay, there's only the metric present, or there's the metric and the scalar field, or the scalar field in its first derivative, or its second derivative as well, whatever. So you have to pick a field content for the dark sector. And once you've done that, you can write down the most general Lagrangian that describes the perturbations of that theory. So a Lagrangian for perturbations is just gives you linearized field equations. It's just quadratic in the field variables. which you can identify everything about. Once you've got Lagrangian, effectively you've got everything. You go away and derive your field equations and work out how the density contrast evolves, or the positive divergence field evolves, things like that, whatever you want. What we can do, for example, is we can impose a symmetry on the background. So we can formulate this on an arbitrary, a background of arbitrary geometry, but that gives you too many free functions. So we say, okay, let the background be isotropic, space on the isotropic, which is fine. That's just saying it's equal W on the background, and that drastically reduces the number of free functions. And then basically we derive equations of state to close the equations of motion. And I'll get to what I mean by that a bit later on, but basically it's the equivalent of W at the level of the background. So W is introduced to close the equations of motion because the pressure is not specified by the conservation equation. It's only specified once you give it an equation of state. So it's W, which is the equation of state parameter, which closes the equations of motion. So our end goal is to work out the equations of state for dark sector perturbations, which are motivated by generic classes of theories. Okay, enough waffle, I think. Bit of maths, what I'm actually doing here. So, at the level of the background, a dark theory will look like this. You have your Einstein-Hilbert term, a matter Lagrangian, and then everything else, your dark sector, is contained within a dark Lagrangian LD. Everything. You can write all modified gravity theories in this way. It's trivial. And the field equation from this action is given by this. So you get your normal Einstein tensor, energy momentum tensor in your known sector, and then your dark energy momentum tensor. So the entire dark sector is in there. Now on an isotropic background, the energy momentum tensor only has two components, pressure and the density. And it satisfies the conservation equation, which fixes the evolution of the density, but not the pressure. This is all standard stuff. So this is the pressure and density of the dark fluid. And this is where the equation of state, W, comes in to close the equation of motion of the background. So the background, the only function which is free here is W. That's the only thing you can measure. At the level of the background, I'll tell you something about the dark sector, yes?
But I can imagine many other equations of state. Why linear? I can play with whatever.
Yeah.
And actually I can even put it on the left-hand side, so there is no then equation of state. So you can assume it's fluid.
Yeah.
So there is so much freedom there.
Yes, there's a lot of freedom.
Choosing one particular which is no better than any other.
Well, this is the simplest way that people are thinking about in the cosmology. So when people go away with observations
and other possibilities, so since we're trying to do this kind of general.
Yes, so
I don't know.
So well, I mean, so this is the background. We're not talking about background anyway from actual things. We're talking about perturbations. So I'm saying this is the way people are thinking. This is the simplest way of doing things. And when people what people measure is W. That's the only thing at the background which people are measuring to tell you about the dark sector. Point being, at the level of linearized perturbations, the action will end up looking will be this. These are the perturbed field equations, and this is the perturbed dark Lagrangian, perturbed dark energy momentum tensor, which also satisfies the perturbed conservation equation. So the question, so we're coming now to this. What's the most general way of closing these equations for particular types of dark theories? And I'll explain what I mean by particular types in a moment. So I said that the Lagrangian perturbations, that's all the dark stuff went in there. So Lagrangian perturbations, that's going to give you linearized field equations, just quadratic in a field variable. So for example, if you had a Lagrangian which had two fields, x and y, this is just really schematic, and the Lagrangian perturbations can only be these three terms. It just all the quadratic combinations of the first perturbations of those fields. So there's all the freedom is now hidden in terms of background field quantities A, B, and C. That's where all the freedom lies. So these things could have indices on them, could be derivatives, whatever. But the point is that all of the freedom in this thing is now boiled down to background quantities. They're only, cosmological background, only functions of time. All the scale dependence is completely specified. Admittedly, if this was utterly general, then that'd be horrific, and that's a freedom here. But I'll show you how we're going to impose some unmotivated choices to completely reduce this. Okay, well, here's the first simplest example. Supposing that the dark set, whatever the dark sector is, it only contains a metric. So not saying derivatives thereof, just a metric. In which case, the Lagrangian perturbations, this is the only form that it can take. The quadratic in the only field available. And the bit which characterizes all of the perturbations is this tensor W. And then if you go away and calculate the field equations for this dark sector theory, the dark energy momentum tensor is this thing here. So the W is coming here. This is the background energy momentum tensor. And there's symmetries which are inherent in the construction of this thing. So this is symmetric and it interchanges these two just because of that, and also interchanges the first two and the second. Anyway, the point is that this thing on an isotropic space only has 5 free components. That's all. So all dark sector theories of this type only have 5 free functions that you can play around with and try and observe. And only functions at a time. We'll actually show in a minute that these 5 don't all feed into the gravitational field equations, into structure formation equations. It's only 3. So this might look like it has 5 free components, but it actually only has 3 when you're looking at cosmological perturbations. We'll show you that in a bit. There's a couple of theories which already sit into this way of thinking about it. For example, mass of gravity, so polypheas, for example. This is a particular form of this W tensor, just in terms of the metric, and the only free thing left is the mass. So this is when you impose that the thing is greater than invariant. Or elastic dark energy, this thing ends up being decomposed in terms of a time-like unit vector U and a spatial metric gamma. And the components of this tensor become specified in terms of the density, pressure, beta is a bulk modulus, and mu is a shear modulus of an elastic medium. I'm going to come back to that particular theory later on. But the point is that there's some theories which fit into this sort of category, but a priori this thing includes everything with that particular field content. So let's go to the next one up. Let's have a scalar field in its first derivative in the field content. So in which case the Lagrangian perturbations is just this, which is everything quadratic. Go away, compute the field equations. The dark energy momentum tensor ends up looking at this. So there's a V away and this term we had before. So this thing on isotropic space only has 2 components. This only has 3. This only has 5. At the moment, this theory contains Lorentz-violating scalar field theories, quintessence, k-essence, and all the previous set of theories I'll make on the slide. And on an isotropic space, you have 10 free functions in there, but it turns out when you impose things like reparameterization invariance, those 10 reduce to 2, and things like that. Okay, those are the 2 simplest manifestations in some sense of our formalism. The whole thing can be extended, and I've done the extensions, but I'm not going to present it just because it's a bit horrific. Well, the Lorentz-violating theories of mass of gravity, I've already shown you a theory which encompasses those 2. Multi-field dark energy, high derivative scalar field theories, so it's point density Galilean theories, you can do that. For example, vector field theories, so including Einstein and all of that, Gaussian tensor theories, biometric theories. You're able to include couplings between the known and the dark sector. So one of the things I was assuming was that that is 0, but it doesn't have to be. If there's a coupling, you just stick a charge in there, and we know how to incorporate all of that. Yeah. So yeah, hopefully I've given you a bit of a flavour of, in some sense, the general maths of what we're doing. Now I'm going to turn it into a usable form, but before I turn it into a usable form, I want to show you something about massive gravity that we found. So this is in a paper we put on the archive last week. So this is the action for that simplest theory where we only have the metric in the dark sector, so this is what it ends up boiling down to. For those who care about these things or know about these things, these delta G's, the metric fluctuations, they are Stuckelberg completed. They contain this vector field which parameterizes for reparameterization violation. On a general isotropic space, the decomposition of this W tensor looks like this. These are all combinations of isotropic tensors. There's 5 combinations: A, B, C, D, and E. Now this xi vector, what this xi vector actually does is it parameterizes for violations of reparameterization variance. So that the naught component parameterizes for violations through time translation, and the I components through spatial translation. So if you were to work out how to make xi naught, for example, decouple, then the theory becomes invariant under translations through time, or if you were to make xi I decouple, it becomes invariant under translations through space. And what we mean by making it decouple is it turns out to be combination constraints on these 5 functions. So we worked out that when xi naught decouples, so what combinations of these things make the xi naught completely vanish from the equations of motion, the 3 things left end up being exactly those for the bulk and shear modulus of an elastic medium. So this is something which is, so the dynamics of general relativistic elastic mediums is not new. It's developed in the 1960s by Brandon Carter and collaborators. And there they laid out how the pressure, the density, and all these things evolve for an elastic medium in general relativity. And it has a particular evolution rule for the pressure, and these things take on particular values. The point being that this particular theory is a mass of gravity. This is a mass term for the graviton, and when you have time translation invariance, it becomes the same as elasticity theory. When the space component decouples, the theory becomes the same as a non-canonical scalar field theory, 3 degrees of freedom, and these particular values make xi decouple. The point being, in some sense, we're not saying anything new about massive gravity here. What we're giving is an interpretation of a massive gravity which has time translation invariance. The only one of those massive gravities is the same as elastic arc energy. The point is that when you think of massive gravity, what you should actually be thinking about is space-time with rigidity. The space-time is elastic. And by elastic, we mean it's a medium with some physical properties like a bulk modulus and how it responds to shear stress and things like that. And it turns out the masses of the gravitons are determined by the bulk and shear moduli of an elastic medium. Okay, let's go back to the program now. I've got all this formalism. How do I actually do cosmology with it and give it to an observer to Cosmo MC over to do something with? Everything that I've said basically just boils down to what is the dark energy momentum tensor. And for all the theories I've talked about and loads of others, for the scalar and metric theories, they just end up being something like this: a Y sum operator, W sum operator acting on these things. And it's just some derivative expansion. So if I specify a particular field content, it'll end up truncating some of these things. You can also, I suppose, truncate in energy scales and stuff like that, but we're not doing that. We're truncating in the field content. These A, B, C, D, E, F, G, H, these are tensors which can all be traced back to something in the quadratic action. So, for example, if you were to find that with data D had to vanish, that tells you about some coupling in the Lagrangian which has to vanish. It tells you about some symmetry about the dark sector, about something about the field content of the dark sector. The point is that the Lagrangian actually combines really hideously into these things here, but it's these things here which are the things which actually affect observables. So sort of in some sense, point number one is that the Lagrangian contains too much information, cosmological perturbations, but it is useful for understanding what the free functions mean in terms of symmetries and couplings of the dark sector theory. Okay, so what I said here, we got Lagrangian perturbations, complete field equations, which is some horrific theory in the fundamental field content of the dark sector, the perturbed fields, derivatives, metric derivatives, things like that. And you take those things and then you work out what are the components of the dark energy momentum tensor are a density, velocity divergence, the pressure, and an anisotropic stress. So you can work out how these things combine to give you the perturbed fluid variables. So they may combine in there. So not all of these components will actually end up being in here. You can work out what they are, I'll show you that in a minute. And just like the density had an evolution equation but not the pressure, it's the perturbed pressure and anisotropic stress which don't have evolution equations. So it's these things which are the free functions. And the whole game is what are these things in generic classes of theories. So let me just outline that again. This is the energy momentum tensor, in general, whatever they are from a theory. Here's the perturbed metric, so this and this is what the perturbed conservation equation ends up becoming. So this is just the familiar structure formation equations with a general energy momentum tensor. It's not particularly new, I'll just write it out, but it proves the point that the naught component of delta U has an evolution equation, and the naught I component, the velocity field, has an evolution equation, but the pressure and the anisotropic stress do not. They're free, they're unspecified at this level. However, if, for example, the theory was combined in such a way to give you the pressure as functions of things which have evolution equations, like the density contrast, velocity fields, the derivatives, the metric variables, so in synchronous cases, the diagonal perturbation and the off-diagonal perturbation, the same for the stress, then the perturbation equations are closed. These things are equations of state. They're taking the state of the system and a particular theory will say how the state of the system is combining to actually close the field equations. So, are there generic forms of these expressions for wide classes of theories? So, for example, in my set of theories where they only have the metric or only have a scalar field, is there a particular form of these things that is always realised? Or, for example, is there a specific form of these things for a given field content? Those are the questions. The answer is yes. Here is what they are. So here's a general example. I'll do a specific one in a minute. Let's take these two expansions of the tensor y and w. So it's got 3 derivatives and 1 derivative in the metric thing. This thing contains massive gravity, 1 derivative scalar field theories, kinetic gravity braiding. It doesn't quite contain 1 density yet, but just for this purposes, this will do. And then we take this theory and we say it has to have second order field equations to avoid ghosts, and it has to satisfy reparameterization invariance. We'll impose that from the outset, and that just reduces the freedom. We don't have to, but we get so many free functions we don't know what to do with them observationally. In which case, you go away and calculate fluid variables, so delta, theta, delta p, and pi. And this is what they come out to be in terms of the field variables. So these are the field variables, these are fluid variables, and there's some matrix here which determines how the field variables combine to give you the fluid variables. It tells you how the field variables are activated into the fluid variables. So all theories whose field equations look like this have an activation matrix of this form. All the things in red are scale independent. The black components only have linear, their scale dependence is a time dependent plus a time dependent times k squared. That can all be isolated. This still has unclosed field equations, but we can just rather this. Well, it's just a case of manipulation now. So you take these things, rearrange it, and you find out that rather than writing delta p, the pressure perturbation, we'll write the entropy perturbation. This is assuming w dot is 0 for simplicity. The entropy perturbation is completely specified in terms of density contrast, velocity field, h dot, and h double dot. There's no extra fields that go into the equations of the state to close the field equations. And this is the closed form of the anisotropic stress. So we're going to delta, h dot, and theta. There's nothing else. There's no h double dot in here. No theory of this kind has a h double dot in here. This completely specifies how the state of the system combines to close the field equations. And these blue things are scale dependent. They're rather horrific, but you can work out exactly what they are. Red things are scale independent still. Here's an example for a particular theory. So let's say here's a theory with a scalar field, kinetic term, and box-wise for the second derivative. And you say, okay, it's got to have second-order field equations. So we search for all the theories inside here which have second-order field equations, and this is all of them. This thing has second-order field equations. It has a name as well, kinetic gravity braiding. This is not new. This is 5-ish years old, I suppose, with this particular name. Okay, so if you take this theory, you calculate what those components are in the activation matrix. It turns out some of those components have to be 0 in this theory. And the entropy ends up looking like this. So it ends up having I've used the fluid equations to sort of rejig some stuff, but the point is that there's a delta, theta, h dot, and then a couple of other terms here. Everything, all the red and the blue, are scale independent. This is the only scale dependent bit. It's k-squared, and these two prefactors are only time dependent. All the scale dependents have been parameterized for, and this sigma is proportional to how this coupling thing depends on the kinetic term. So if this vanishes, which just removes all of this gunk here. So all the freedom in this model is parameterized by 7 time-dependent functions. These are functions, okay, at the moment, Monte Carlo over 7 is quite a lot. We're not suggesting that at all yet. I'll give you a simple example in a minute. But the point is, if you're to find out that sigma equals 0 was the only thing consistent with data, that told you something really important about a symmetry in the Lagrangian for the dark sector. Okay, we're not really claiming this is absolutely doable yet, but I'm going to show you something which is. So this is one of those, the simplest possible theory. These are the equations of state for the metric-only theory. The entropy perturbation only has the density contrast in it, and the anisotropic stress only has density contrast and eta, which is the off-diagonal metric perturbation. And so there's 3 free functions of time only, and that's it. Kappa, lambda, epsilon, that's it. All theories of this kind are specified by the values of these parameters. All theories of this kind, where this is a scalar field theory with real parameterization variance imposed, so chi is x is the kinetic term, have only 2 free functions, and pi vanishes for this theory. So it only has delta and theta in it. It doesn't have delta dot, it doesn't have h dot, nothing like that. It only has these things in it. So all theories of this kind just contribute towards values of alpha and beta. And I can go away and compute what these values of alpha and beta are as functions of the actual Lagrangian if I wanted to. So for example, all theories of this kind, so this is pure k-essence in some sense, has beta being exactly the number 0. And all quintessence, quintessence, so that's a canonical kinetic term, have alpha and beta being exactly the number 1, regardless of the value of v. That's how it conspires. So varying alpha and beta sort of moves you around the space of these theories, where particular values push you into certain regimes. But the point is, you can Monte Carlo over alpha and beta, and that'll tell you something. And alpha and beta, there's just 2 not there. In general, they're functions of time, but we've worked out their values. Basically, they're multiplied by things which look like slow roll coefficients. So we as a first approximation, take them to be constant. Of course, that's the simplification, but you can't go parameterizing over. We don't know how to Monte Carlo observationally measure arbitrary functions of time properly. So just these theories again. So kappa, lambda, and epsilon, and alpha and beta. This is how they're composed in terms of things in the Lagrangian. So D, E, B, etc. They're all things which are in the Lagrangian, but they combine in some horrific way. Well, this isn't too horrific, but combine in some way to give you the things which actually affect the field equations. This is what they are in massive gravity theory. So these MIs are the mass terms of the gravitons, and this is the bulk and shear modulus of an elastic medium. So they take on particular values. But again, all you're doing is you can only measure the values of epsilon, lambda, and kappa. And these scalar field theories here, alpha and beta, in terms of the Lagrangian, you can work out what they actually are. I want to point out one of the things that is relatively popular in the literature is to use entropy perturbation, which looks like this. So basically, they set beta to be the number 1, and then vary what you'd call the sound speed of the scalar field. Now, this is only a sound speed when it's the number 1. When it's not the number 1, you're not in this quintessence scenario anymore, so you're not looking at quintessence. And when this is not the number 1, the number that should sit here is also not the number 1. So you need to be varying both. And this analysis has shown that. Okay, so what do these parameters actually do to observables? Let's go away. You can stick this spot into CAM, turn the handle, and let's compute some spectra. Okay, so this is that no-extra fields case, the L of G only case. Kappa was one of those parameters. Dial its value, compute the power spectrum of this is PK. So what you can see here is that the very large scales are relatively unaffected. Small scales get power enhanced, the small values of kappa, but middle scales get messed around quite a lot. The point being, once you have data on here, error bars, it tells you how much you're actually allowed to vary kappa by. This is elastic dark energy. So the elastic dark energy theory was one of those metric-only theories, a particular combination of them. It was the theory which had the elastic medium. And the only parameter, the bulk modulus and the shear modulus just combined to produce the sound speed of the elastic medium, CS squared. So, by the way, all these plots have W of minus 0.9, which is okay, just to prove a point. So dialing down the value of the sound speed has the effect of increasing power on middling scales. So what this is saying is that whatever the dark energy is, when its sound speed goes very small, it starts clustering a lot on middling scales. CDM does this, and basically when CS squared becomes 0, it becomes basically another CDM component, and you can rule it out. You can put a lower bound on CS squared because the peak will just start to rocket. Okay, that's the sort of more traditional spectra. Here's the gravitational lensing spectra of the CMB. So CLDD. So this is dialing the sound speed. So it changes only the large. Well, it changes up to about here. I'll give you some more qualitative things in a minute, but there's sort of deviations along here. This is the DT spectrum. So this is the correlation between lensing and temperature fluctuations of the CMB for alpha beta model. So this is varying the two parameters in that scalar field model. And so it messes around the large scale power, but not the small scale power. Now, one of the problems is here, observations are cosmic variance limited, which means you sort of have a fundamental error bar and something over here. So you'll never really be able to distinguish certain theories if they only modify things on the large scales. That's something we take into account in a bit. So here's some relative differences between some scalar field models. So take a fiducial quintessence model, and then we vary the values of alpha and beta and compare the spectrum to that. What's the delta CL? So this is dialing some parameters. So this is the delta CL. So you get some shifts, but only of the order of 3 or 4% on this value of alpha and beta. And all these lines are basically on top of each other. There's a huge degeneracy with this particular spectrum. It's the DD spectrum. But the DT spectrum seems to break the degeneracy and varies things by a bit more. So sometimes it enhances power, and sometimes it ends up suppressing power. But fundamentally, these are really small effects. The scalar field models with this alpha and beta parameterization have really small effects on the lensing spectrum. Okay, so this is now all the metric-only theories. So this is the elastic dark energy theory. So this is the DD spectrum again. This is varying the lensing spectrum now by about 30%. This is really quite a large variation when you start dialing through theory space. This is the DT spectrum, so the temperature lensing correlation, and it gives you actually a really rather distinctive, different type of spectrum. These are sort of get some weird bumps and lumps in them. These are quite distinctive. Again, this can vary by up to 100% if you dial CS squared large enough. So you can start to use data to rule some of these things out. This is kappa, so this is one of those parameters of metric-only theory. So again, DD spectrum, it's not a large variation, 8% or so, but the DT spectrum has quite a signature on this, is sort of going all over the place, up to 60% and keep changing it. So the point being, what we've got here is a set of parameters which mean something in terms of theories, and then we can work out what sort of things they actually do to observables. And do you actually have a chance of picking up these differences or not? So this is now some preliminary stuff I did 2 days ago, really, so it's rather crude at the moment. We basically just compute likelihoods for these things. So this is log likelihood. These are different sorts of spectra. So the red line is TT, unlensed, the TT lensed, DD spectrum and DT spectrum. So this is the alpha beta model. This is keeping beta fixed at the number 1 and varying log 10 alpha. And so the log likelihood only becomes sort of something which you can actually distinguish above this. There's sort of cream shading here, but it only becomes really observable in the DD spectrum. The TT spectrum will always you'll never be able to really you'll never be able to use each spectrum to distinguish the models. This is a elastic Lagrangian model, so again, here's the 0 line. So things above here you'll be able to distinguish. So when CS squared becomes so low, almost, well, so the TT lens spectrum and the DD spectrum become really useful for distinguishing theories, but the TT spectrum is just a bit, well, the TT and lens spectrum is just a bit naff. DT spectrum, just ignore it, there's just sort of it's divided by some 0 somewhere, it's just a trivial artifact. And here I've fixed W to minus 0.9. So all these effects become chronically enhanced when you start taking W away from minus 1. So this is now varying beta and log alpha and alpha beta thing, and computing the likelihood sort of 2D surface in some sense. So whenever it gets to about the number 0, you'd be able to start to distinguish the models, and everything in this sort of space, crudely put, is detectable and distinguishable, by which I mean the value of alpha will be, but the value of beta doesn't really have much of a gradient in it on this particular range. But all of these models will give you something which basically looks the same, so you're never actually really going to be able to detect the differences which are given by these models. This is now a rather qualitative diagram of what's going on here. So sound speeds and kappa, for example, alpha and beta, and these are different spectra. So yeah, large scale, medium scale, small scale. Does varying this parameter affect a particular spectrum and on what scale? It's very qualitative. But the point being that CS squared mainly modifies medium scale power and then large scale power for the angular power spectra. Kappa varies large and medium, but most scales on the DT spectrum. Beta is pretty naff, to be perfectly honest. It's not a great distinguisher. The part of the problem here is most of these things actually affect the large scale power of spectra, which is cosmic variance limited, which is a bit of a problem, but that's fundamental. We can't really get away from that. What will help is get more data, obviously, to shrink error bars. So Planck, when it comes out, the CFHDLS stuff, which we've got, but we still need to analyse properly, and then obviously Euclid in the distant future. Right. Coming into land now. Where I started off was perturbations of the dark sector need parameterizing. People are doing things, but they're producing parameters and constraints on the parameters which it's sketchy what their meaning is, putting it politely, I think. And their methods and parameters are not particularly physical. It doesn't really tell you much about theory space. What we've done is constructed Lagrangian perturbations from a field content and derived everything from that. And that ends up giving you, for example, a maximum amount of freedom. There is no more freedom than a particular thing that we can work out. And then the way that we've packaged our parameterization is using equations of state for dark sector perturbations. We've done that for different field contents. And we say if the dark sector has this field content, this is the only way, this is all the number of parameters that you can measure. There's no more parameters to be measured for this field content. And it's a small number, so one of them had 2, one of them had 3. These are all things which you could, and we're about to Monte Carlo over. And you can go away, you can compute the signatures and do loads of CAM work and that sort of thing, and you can go and constrain the parameters with data. This is still a work in development. We're still looking at the stabilities of these things, what regions of parameter space correspond to pathological things, and that sort of thing, and how do we encompass more general things without introducing too many free functions. This is all stuff we're still working on. So yeah, I'll end there. Thank you very much, and if you've got any questions.
Is this different from what the Chicago people call parameterized post-Friedman relations?
PPF. So there's two versions of that. Are you talking about the Who-and-Sawicki one or the Hedger-Ferrero one?
Because I've only heard about the Who.
Who-and-Sawicki. Okay, so Who-and-Sawicki, basically what they do is write down some parameterization. It works for particular models of like F of R theories, but it sits, unfortunately, I think it sits into the class of theories where you are parameterizations where you're constraining parameters and you don't really know what it is that they end up meaning. So they know what they mean for particular values.
Well, at least there's still some of the things, but you're saying you want to have, decoupled parameterization of all linear perturbations.
Yes.
But
Okay. Yes.
They use the same words as you do. So
Yes.
how does it actually?
Yes. So the difference between us and them is we've got a parameterization that we know exactly what it is that the parameters mean in terms of a field content. So when we say here's the parameters which you should be constraining, I know exactly what sort of dark sector theory that means in terms of what field content it has and how couplings in the theory combine to construct those parameters. Now they can do that for certain theories, but in general I don't think that's true for them. In some the game is really let's produce a physically meaningful and obvious parameterization, and that's what I believe this is.
How strongly were the results affected by the assumption of W equals -0.9? Like if it was say -0.95, are the
Yes.
deviations very small?
Yes, the deviation becomes suppressed when W gets close to -1, but that would be inherent in everything. So the chances of you detecting something as it gets closer to -1 decreases. That's generic. I don't know a way around that. You're always going to end up suppressing things, and for that, basically, you just need really high quality data.
You mentioned dark matter as a motivation or something that was invented as an epicycle to deal with data. And for that one, there happens to be a reasonable CDM theory which has particular, I suppose, it's kind of a trivial case where all these values are bigger equal to 0. But on the other hand, in detail, again, I thought the claim has been that all the modified, the reason why people like Wayne Fu, when they deal with modified gravity, they claim everything is nonlinear and any linear combination will never, despite being within order of magnitude of what's going on, just like he argues if you apply the linear theory to cold dark matter, it only works when it really stays linear, whereas in nonlinear scales, none of those closures are good to order unity. But you're saying that that's not true. You're saying that what he's saying is incorrect, and then in fact those f of r's, which he claims are intrinsically non-perturbative and require you running non-local n-body simulations to talk about the last scale correlation function. So you're saying what he's saying is incorrect.
I'm not about to say when who's wrong. No, I'm not. We're only talking about things on the linear scale, so we don't want to go to too high L or too high K. It's going to break down. I think one of there is sort of a philosophical thing here. So we're saying whatever it is that's conspiring to construct whatever we see, we can model it in this way.
Well, but Wayne says we cannot, right? So he says on large scales, in the case of a modified gravity theory, because chameleonhood on small scale, everything all hell breaks loose on large scales, and therefore all linear descriptions are just not relevant, and you've got to run these, even on large scales, you have to run these, non-linear n-body simulations.
Yes. Well, I'm not convinced that nothing can be gained from the linear perturbations. So, if you want to try and use this to construct a model of the fundamental theory of modified gravity, then you've got to be able to do all of what you just said, what they're trying to do. But we're trying to sort of a phenomenological parameterization of the large scale stuff. And so what we're sort of saying is, it's got to come down to GR at solid system scale. It's got to reproduce what it is that you see, and that constrains the values of the parameters that are allowed to be.
Well, but he uses the same word, but he comes to the opposite conclusion, right?
But then you're not allowed to use linear perturbation theory.
In his case, yes, he claims that, right? He claims
yes,
that
I haven't followed his argument utterly carefully to be able to say what about it. I think there's still a lot to be gained from linear perturbation theory and using cosmological data sets like lensing and CMB to constrain properties of the dark sector. I think there's still a lot to be done with that.
This is maybe a related question, but how do you know the region of validity of your field here? Do you want to do some energy cutoffs or
yeah. So again, that comes down to so when people say they're doing effective field theory, they usually say they're using some cutoff in terms of like an energy scale or whatever, and that sets what your theory is valid for. What we're doing is we're saying, okay, we're doing an effective field theory, but that's not how we're constraining what terms we're allowing. We're saying the underlying physics, when it's being coarse-grained over, it can be described by something like this on these scale, on cosmological scales. So we're not talking about constructing a fundamental field theory. And so we're not having to sort of worry about those age scale cutoffs in terms of when do we believe this and when do we not. We're talking about parameterizing over the large scale perturbations, and that there is a difference in sort of mindset. So we're not doing fundamental stuff. We're doing this phenomenological thing. I mean, so the elastic dark energy model, I didn't really get time to talk about too much, but basically it's a way of saying, okay, you've got some really complicated microphysics, but it all combines in a relatively simple way to just say it ends up being a medium. I mean, so I'm used to the idea of there's horrifically complicated physics going on inside a table, but I just say it's a table with this bulk modulus and shear modulus, and I know how it responds if I kick it. And I don't care about how it actually does it on the inside. And in some sense, that's what we're doing here with cosmological perturbations and the gravitational theory of the dark sector. It's combining in some horrifically complicated way that you never care about. You just want to see what's the physical property of the medium of the theory which you're able to observe when you kick it.
All right.